Okay, so this is our neutral axis. Okay, so this is our neutral axis. Okay, and for this case, what we have down here is we have no load. No load is applied, right? So the next one that I'm going to draw by side is we're going to put a load. Okay, so when we put a load, and this is only in the elastic region. Okay, so now we put a load, and because of the load, so we apply an axial load. Okay, so I will call my load in the y direction, and it's going to be based on this transformation: x, y, and rotation about z. Okay, and then we have our neutral axis again, right? So now what you see that is different now is the length is different now. This is your L1, okay? And this distance from here to here is L1 minus L0, and this is known as our change in length. Okay, and it's always L1, the new length, minus the original. Okay, you don't flip it around. Okay, it does not work like, not like, okay, depending on the direction of the wind, okay, I'm going to flip it around. No, and I'll tell you why no later. Okay, so when a load is applied, there's a change in length, right, which is our delta 1, is based on the new length minus the original length. Okay, so as I mentioned before, in the elastic region, right, material will obey Hooke's law. Okay. So what do I mean by the material will obey Hooke's law? So if we were to focus on the elastic region now, yeah, if we were to focus on the elastic region, so stress strain curve, right? So this is the elastic region, right? So it's a straight line, and at this point over here, this is your stress U. Okay, so if you look at in the elastic region, okay, we know that this slope, right, this slope over here is your E, right? And based on Hooke's law, right? So I'm going to write up Hooke's law now, right? So Hooke's law states that stress is equal to slope multiplied by epsilon. Okay. So for this case, if you look at the parent function mathematically, if you look at the parent function, right? Parent function mathematically is y-axis is equal to mx plus c, right? For this case, our C is equal to 0, our gradient is E, our x is our variable is epsilon, and our response is our stress. So that's where we have this formula. Okay, so this is what we call Hooke's law. And what we realize that in the elastic region, right, in the elastic region, you have a linear response, right? It's a straight line, yes or no? Okay. So now coming back to Hooke's law, okay, we're going to apply look at Hooke's law. So we have stress is equal to E epsilon, right? That is what we have. And then, so I'm going to call this equation number, I could not remember what equation number we are in now. I don't know. So yeah, so this is equation number 2. I'm going to call this equation number 2. And we know epsilon, right? We know that epsilon is equal to L1 minus by L naught divided by L naught, right? So if we go back to our diagram, right, L1 minus L naught is equal to delta L. And this is also equal to what? This can also be equal to our deflection, right? That is equal to deflection, right? So if I were to come back to this equation over here, where epsilon is equal to deflection divided by L naught, okay? So this is equation number 3. So we're going to substitute equation 3 into equation 2 now, right? So we have stress is equal to E deflection over L naught, okay? Deflection over L naught. And we know, note that stress is equal to P in the y direction divided by A, right? So we have an expression is equal to stress of P in the y direction divided by A is equal to E deflection over L naught. So finally, therefore, deflection is equal to P load in the y direction L naught over AE. Okay. So we have derived our equation, and this is known as our equation number 4. Okay, we just derive our equation. Okay, where deflection is equal to P y naught P y L naught AE. Okay, so now because we have derived, okay, now we are going to write. I'm going to copy this, so because I have more space down here. We're almost done for first break. Okay, bear with me. Right, so we have this expression over here. Okay. So equation 4 is only valid when, okay, when what? Okay, when material is is loaded in the elastic region only. Okay, then you can use PL over AE. Okay, and it's only valid. So we know that it's only applicable in the elastic region. Okay, and this is critical. Okay, when stress and strain has a linear relationship. Okay, the strain is small and finally this is only true under axial loading condition only. Now some of them might say, hey, where did you get all this from? Okay, where do you get all this from? So when we started deriving, right? The first point is from where? The first point is from here. So the first point, right? This is only valid in the elastic region. We draw this graph and we say it can only operate in the what? Elastic region. Okay. When stress and strain has a linear relationship, where did that come from? Okay, when stress and strain had a linear relationship is this, right? So when if and only if they have a linear relationship, right, then we can apply what? Then we can apply Hooke's law. Okay, then we can apply Hooke's law over here. The strain is small. Okay, so where do we get that from? Okay, so the deflection induced by the load has to be small, right? So small over here means before, okay, U strain. Okay, so the value has to be smaller than the U strain. Oh, not before. What am I writing? Smaller than the U strain. So if some of you ask, so what is this? What is this value actually? So if we look at a standard steel, okay, so let's say for a steel product, Young's modulus is equal to 200 times 10 to the power of 9 Pascal, or 210. The stress at U. So if we look at a medium strength steel, is about 450 times 10 to the power of 6 Pascal, right? So when we calculate the strain, I know I'm going over, give me like 2 more minutes, okay? So the strain is equal to stress Y divided by E. So this is equal to 450 times 10 to the power of 6 divided by 200 times 10 to the power of 9. Okay. So 450 power of 6 divided by 200 power of 9 is equal to 2.25 times 10 to the power minus 3. Okay, so the strain is small. And then the final condition is under axial loading condition only. So under axial loading condition only, where did that come from? Okay, so that come from this formula that we just applied, where Py over A. So Py over A is only valid for axial loading. Okay, I'm going to stop recording over here.